The next chapter we're going to study is optical instruments. Now you must have heard of optical instruments like a microscope, a telescope. Even the human eye is an optical instrument. So how do they all work? And how can we solve IIT problems related to telescopes and microscopes? That's what we're going to study in this chapter. So let's begin. The first thing we'll study is the human eye. The eye actually consists of a lens and a retina. These constitute the part of the eye which help us see. The lens of the eye is called the cornea, and it's a convex lens. This is how you spell cornea. Cornea. One interesting fact about the human eye is that, the distance between the lens and the back part of the eye, called the retina, is fixed. And another interesting part is that wherever an object is placed, when it gets refracted through the eye lens, its image is always formed on the retina. So the image distance is fixed in case of a human eye. So I may place an object here, or I may place an object here, or I may place an object here, but the image of this object will always be formed on the retina. So this distance is actually equal to V, the image distance, and this is fixed. Now if the image distance is fixed, how is it that for different object distances we can still see the image at the same place, the retina? This is possible because U and F vary. The object distance varies, but the focal length of the eye lens can also be varied. So remember the formula 1 by V minus 1 by U equal to 1 by F. U and F vary in the case of an eye, and V is constant. Now how does the focal length of the eye vary? There are these muscles here, here and here. These muscles are called ciliary muscles. Ciliary. Now these muscles contract or they expand to change the focal length of the eye lens. So when the object is far away, then the rays on the eye lens, they fall like this, parallel to the principal axis. And then a very big focal length will also do. A lens with less power will also do, because then you don't have to really make an effort to converge the rays. They're parallel and you can converge the rays like this. So the focal length when the object is at infinity, it's high. When the object comes closer and closer to the lens has to become stronger, it has to become more powerful. And when the lens has greater power, it has lesser focal length because it converges rays faster. So when the object is brought nearer and nearer to the lens, let's say when the object is brought here, then the lens must have a lesser focal length and a greater power, because in the same distance V, here also the rays got converged in the distance V, and even when the object has been brought closer to the lens, in the same distance V, the rays again have to converge like this. So clearly these rays are diverging, right? And the rays will become more and more diverging as the object is brought closer and closer to the lens. So the lens must become more and more powerful as the object keeps approaching the lens, right? And it's the ciliary muscles which contract, to provide more power to the lens. So you can say that initially, when the object is placed at infinity, the lens has a shape something like this. And as the object is brought closer, the lens becomes fatter because its power increases. And when, you hold something very close to your eye, that's when the ciliary muscles contract the most. And the lens is almost circular, like this. Now, when the object is brought to a distance D, a limit is reached. Because, you can't decrease the focal length or increase the power of the lens infinitely. You can't say that I'll bring an object 1 millimeter close to the eye and the ciliary muscles should so contract that the eye lens forms an image still on the retina. After all, if you bring an object here, look at the rays, they're diverging so much. How can they be converged in such a short distance, in this distance? So there is a certain distance called D. This distance D is called the least distance of distinct vision. Least distance of distinct vision. This means that when you bring an object up till a distance D from the eye lens, it's visible, it's clear, and its image is formed in the retina. But if you bring the object closer than D, no matter what you do, the image of the object will not be formed on the retina, because no matter how much the ciliary muscles contract, they will just not be able to contract enough to make the lens powerful enough to make the rays converge at the retina. Up till D, the rays converge at the retina. Here, this is the retina. But when you get closer than D, the rays converge after the retina, like this. So no matter what you do, you'll not see a clear image. Even you must have noticed it, Let's say you hold your finger in front of you and you keep bringing that finger closer to your eyes, closer. There will come a stage when no matter, how hard you strain your eyes, you cannot see the finger clearly. This distance D varies with age. For example, for teenagers, it's around 10 centimeters. For people around the age of 40 years, it's around 25 centimeters. For people around the age of 50 years or 60 years, it's around 40 centimeters. So, they say that old people cannot read small text. They cannot read books without spectacles. That's because their least distance of distinct vision has increased. So, they can't even see an object that is 40 centimeters away from them clearly. That is why their vision becomes weak. Another interesting point about the eye is that the image formed by the eye is always real and inverted. It's at the retina and it's real and inverted. As you can see here, the inverted image. You must remember this property. So as you can see here, as the object is brought closer and closer to the eye, the size of the image here increases up till a distance D. And D is the least distance of distinct vision. Let's have a look at an animation that will show you even more clearly how the eye forms an image. So as you can see in this animation, as the distance of the object from the eye is changed from infinity to D, the eye keeps on, expanding at the center and the size of the image keeps increasing. Have a look at it again. As you can see, the ciliary muscles are contracting, the eye is getting bigger and bigger in terms of the power of its lens, and the image size is also getting bigger and bigger, up till a distance D centimeters. And the image is being formed on the retina. There you go. Now let's study about some defects in the eye. The defects in the eye are mainly caused because the image is not formed in the retina due to some reason. It's formed before the retina or it's formed after the retina. Let's first study about myopia, a common defect in young people. In this case, the image is formed just before the retina. That is, the rays converge before the retina. Like this. This generally happens because of over-bulging of the eyeball. You see, the lens of the eye becomes so powerful that it converges the rays before the retina itself. This defect is called, as I just said, myopia or short-sightedness. In myopia, you cannot see far away objects clearly, but you can see, objects which are placed near your eye very clearly. Most young people, as you already know, have this defect, and all of us wear glasses or we have contact lenses to correct this defect. So how do glasses or contact lenses help correct myopia? Well, you see, if you had a concave lens here, like this, then that concave lens would diverge the converging rays just so much that the rays now meet at the retina. So if you choose a concave lens of a specific power, then you can make the rays converge at the retina. So the corrective lens in case of myopia is a concave lens. Another interesting defect is when the rays converge after the retina. This generally happens with old people. You see, the lens becomes weak and the ciliary muscles, they become very weak. So they lose their power to contract and increase the power of the lens. So no matter how much they contract, they're still not able to converge the rays at the retina. They're too weak. And because of the weak ciliary muscles, there's difficulty in converging and the rays converge slowly, after the retina. This defect is called hypermetropia or farsightedness. This is common in old people. You see, what actually happens in this case is that people cannot see things which are very near their eyes. That's because, when things are very near your eyes, that's when the ciliary muscles have to be strong. They have to converge those diverging rays from the object fast. But that doesn't happen for old people. And that's why, hypermetropia is what old people suffer from. So how can you correct hypermetropia or farsightedness? You can do that by using a convex lens. You see, your ciliary muscles aren't strong enough, so the convex lens will aid the ciliary muscles in converging the light rays. And if you use a convex lens of the appropriate power, it will converge the rays exactly at the retina. There you go. That's why, when young people wear lenses and they cannot see far away things, they say, they have negative lenses because a concave lens is used. And when old people wear lenses, to read newspapers and to read things which are near them, they have a positive power lens, like they have powers like +2, +3, +4, because they use a convex lens. So we've talked so much about the eye. Now let's solve a problem and make things more interesting.